will be Anita Buckley, who will be talking about an algebraic language for specifying quantum networks. So go ahead, Anita.
Hi, my name is Anita Buckley, and I will talk about an algebraic language for specifying quantum network protocols and how to verify their behavior. This is a joint work, and I'm very happy that all my collaborators are here at PLDI. Quantum networks are networks connecting quantum-capable devices. All the previous talks in this session were interested in what's happening inside quantum devices. Now we connect these devices together and make them communicate with each other. Each device in a quantum network will have a few of so-called communication qubits designated to establish connections with other devices in the network. By being connected, we mean that distributed devices can share entanglement. If you're not familiar with entanglement, think of it as communication qubits sharing a correlated random secret. Quantum networks bring benefits. For example, scaling of quantum computation that is also part of IBM quantum roadmap. Another benefit of quantum networks is that they provide secure communication with killer apps such as teleportation and entanglement-based quantum key distribution. Quantum networks are coming into reality. Just as I was preparing this talk, reports came out of quantum nodes built in the US, China, and Netherlands. Now, computer science becomes essential to drive further advances in this field. And with this purpose, we are here. Quantum networks rely on Bell pairs, which are the fundamental entanglement resource of quantum networks. Bell pair is a pair of entangled qubits that are correlated by what we called earlier shared random secret, or what Einstein called spooky action at a distance. We denote a Bell pair by a tilde connecting the nodes that contain entangled qubits. One limitation of Bell pairs is that they carry no control information. Thus, quantum networks have to be built on top of classical ones. Classical networks consist of end nodes that are connected through switches via classical channels. On top of this, quantum networks have separate quantum channels, quantum-capable end nodes, and repeaters to overcome short distances. Some of these nodes can also act as quantum source, where Bell pairs are created locally, such as the two indicated with black star on this picture. Now let's have a look how protocols run on such architectures. From now on, we will represent network's topology as a graph. In a classical network, a packet, the information carrier, is forwarded from source S to destination, say D1 in this example. The packet is forwarded through switches hop by hop, 1, 2, and 3. In quantum networks, on the other hand, qubits cannot be forwarded over larger distances due to the decoherence and the no-cloning theorem. Let's have a look at a simple protocol that generates end-to-end Bell pair between nodes A and E. We started by creating a Bell pair locally at E and another one locally at C. Next, we transmit a qubit of the EE pair to D and each of the qubits of the CC pair to its neighbors, A and D. Then we perform entanglement swap. This operation is Bell measurement that exchanges the two Bell pairs into one over larger distance. This way we generated end-to-end Bell pair AE. To overcome qubits decoherence and short lifespans, we perform as many operations as possible in parallel. Consider the next protocol example that will generate end-to-end Bell pairs, one between nodes A and D, and another one between B and E. The protocol will run in 3 rounds. In the first round, we generate 4 Bell pairs locally, 2 at E and 2 at C. On the right, we write the execution histories that record Bell pairs that were produced in each round. And in gray, we annotate the action that created them. In round 2, we in parallel transmit the qubits to their neighbors. And in the third round, we perform the swaps to obtain the green Bell pair AE and the purple Bell pair BE. Given that quantum networks work like this, we need to make sure that they behave as intended. We should be able to answer questions like, does a protocol establish Bell pairs between the specified end nodes? Are two protocols equivalent? Can a protocol execute with a given number of resources? Or can protocols run in parallel without interfering with each other? As a solution, we provide formalism to answer these types of questions, similar to what NetCat did for classical networks, which also inspired our work. We designed a specification language for end-to-end Bell pair generation. The name BellKAT alludes to Bell pairs and Kleene algebra with tests, KAT. BellKAT's key features are its syntax and semantics that provide abstraction for quantum network primitives such as the actions we met earlier. They model multi-round behavior as seen in the protocol example by capturing concurrent resource sharing and synchronization at the end of each round. BellKAT's algebraic structure is based on Kleene algebra with novel axiom capturing ground synchronization. And we also provide formal proofs of soundness and completeness and a decidability result for checking semantic equivalences. In what follows, we will introduce the language components in this order. Basic actions are the basic building blocks abstracting protocol primitives. We can think of basic actions as functions defined in terms of required Bell pairs and output Bell pairs. I'll explain the definition on the swap example that requires Bell pairs AD and DE to output Bell pair AE. So basic action takes as an input a number of Bell pairs and checks if it contains the required Bell pairs. If yes, like in this example, then it produces from it some new output Bell pairs, shown in green, by consuming the red required Bell pairs. And the remaining Bell pairs are left untouched. Now let's see how the same swap acts on an input that does not contain required Bell pairs. This input contains the required Bell pair DE, but not also AD. In this case, all the Bell pairs remain untouched and remain available to another action. This way, basic actions abstract all protocol primitives. For example, swap requires two Bell pairs to output one over larger distance. Transmit requires a local Bell pair and can only forward its qubits to the adjacent neighbors. Create is interesting because it requires no Bell pairs to output a local Bell pair. Wait preserves Bell pairs for one round. And fail drops Bell pairs. Next, we combine basic actions into BellKAT expression to build protocols. They consist of basic actions with two constants for abort and for skip, and they are combined with non-deterministic choice, sequential composition for transitioning through the rounds, and Kleene star for iteration. We also have parallel composition and ordered composition that it's just a variant of parallel composition where P always has priority over Q when grabbing Bell pairs. Remember the protocol that generated end-to-end Bell pairs AE and BE. Here is how the protocol is expressed using the syntax that we just introduced. And this is BellKAT at a glance. For the sake of time, we only highlight some interesting design choices we made to address quantum network particularities. We designed BellKAT syntax and semantics to faithfully model quantum network behavior, starting with basic actions. The problem with basic actions is that we cannot express every protocol as a unique combination of basic actions, which is crucial to obtain normal form of protocols. Thus, we break them down into atomic actions that act the same as basic actions, just that these abort if the required Bell pairs are not available. Moreover, atomic actions are guarded by tests that additionally check for presence and absence of Bell pairs. As you know, it is highly non-trivial to come up with sound semantics of parallel programs. We defined multi-round semantics that returns multi-sets of Bell pairs that can be produced by a protocol. We established it through single-round semantics that in addition keeps track of freshly produced Bell pairs. We base BellKAT's algebraic structure on the standard Kleene algebra axioms. But these are not enough to model synchronous concurrency. So we extend them with synchronous Kleene algebra axioms and some network-specific axioms. We also prove formal results. As mentioned on the previous slide, we obtained normal form of protocols, which was crucial to prove soundness and completeness with respect to single-round semantics. For multi-round semantics, we prove soundness and completeness with respect to the standard interpretation that can be thought of in terms of traces of atomic actions. This leads to the proof of soundness of multi-round protocols. As an interesting aspect, we cannot obtain completeness for multi-round protocols, as is usually the case with concurrent systems. On top of this, we obtained a decidability result for checking semantic equivalences in the presence of network constraints with respect to the number of available qubits. With this result, we can answer questions like we asked at the start. For example, the property, does protocol P always or never generate an entangled Bell pair, is expressed with these semantic equivalences. We also invite you to verify more protocol properties with our BellKAT artifact. To summarize, we designed BellKAT language to specify quantum networks. We proved soundness and completeness of BellKAT's axioms. We obtained decidability result for checking semantic equivalences. And we built a prototype tool for automated reasoning about protocols, also available at GitHub through this QR code. And with this, I thank you for your attention.
Thank you for the talk. I'm surprised that you can reuse the Kleene algebra axioms because of distributivity and idempotency of Kleene algebras, and which seem incompatible with quantum.
Very good question. Have a look at the synchronous Kleene algebra axioms. They do not have. We have to remove idempotency. Yes. We do have Kleene algebra axioms, and if you remember our example, we had rounds, right? And the round, I can only sequentially transition through different rounds, which has no interleaving. So all the interleaving is done within, with the parallel and ordered composition within single rounds. This is how we kind of constrain our algebra to model and not run into problems like you pointed out. Mm-hmm.
So one of your original questions was about equivalence of two protocols that you can
Yes.
ask. Do you have like an example or an experiment where you try two different protocols and to see whether you can prove that they're equivalent or not equivalent.
So now, first we have to clarify which equivalence we're talking about. Either axiomatic equivalence with their axioms, and then we also have the semantic equivalences that I give at the end, right?
Yeah.
With the presence of the, maybe here, this is the multi-round semantics, and this N0 is I constrain the inputs that I can provide as a...
Okay, so you make your choice. Do you have an experiment in one of these settings?
Well, we have the artifact that you can just provide different inputs and see,
right.
If they are equivalent.
Yeah, so I'm wondering whether you had like your standard example of two protocols, you try it, and then one way or the other you find out that they're either equivalent.
Yeah, we have maybe I have them in, I'm not sure if I have them in protocol. So the example I have given you, right? Yeah. I'll just try to, it was very straightforward. I transmitted as far as the adjacent neighbors, and then I did the swaps. Yeah. And one of the transmissions was that I transmitted local qubit to each neighbors. But it could easily be that my network can only transmit one of the qubits and the other one has to be kept in the memory. So I will need an additional swap to overcome the first step. Right. So with this semantics, the two protocols would be equivalent.
And you can prove that?
Yes. Yeah.
That's great.
All right, let's thank Anita again.